Hello and welcome to another video, another deep dive debugging video, in fact, where we're going to dive into how I broke Sentry's test suite in a surprising way and ultimately figured out why it broke. And, well, I haven't fixed it yet, but we'll get to that conclusion at the end. But anyway, let's jump into it. So, basically, the start of this is this pull request here, where I know I preach, like, only do one thing at a time, and then here I go. Upgrading two things at once and ultimately getting burned from it. But this PR seemed pretty innocuous on its own. I upgraded pytest and upgraded pytest Django, and flaky also got upgraded. It's dependency. And seemed pretty straightforward, and the tests all passed when I did it, so I thought everything's great, right? Merge this PR and move on with my life and do other things. But it turns out that this PR was not so great, and so it got quick reverted. Actually, I should probably make a video on this quick revert because I actually think it's very good and one of the things that has drastically improved development at Sentry. Anyway, one of my teammates noticed that all of the tests were failing. This was the suspect and ultimately was the cause, and so it ended up getting reverted, despite my change passing on pull request. And if we look through, show you the same workflow that I did. If we look at the commit, we can actually find the reason it got reverted. No, that one's still green. This one's red, and we can find the CI output for the reason it failed, or the reason it was reverted, and the problem that it caused. And oh my, did a lot of tests fail. In fact, so many tests failed and so many retries were attempted by our retry plugin that GitHub Actions actually timed out this job at an hour, and usually it takes a lot less than that. But you can see here that at the beginning, the tests seem pretty fine. They're all passing. And then at some point, they just start all failing. And the first thing that bothers me about this is it's some amount of flaky behavior, because it passed just fine in my pull request. But later on, some of the commits on the mainline branch were failing like this. And I assume some pull requests were failing in the same way as well. And so it's a flaky behavior, which is even more annoying. So I guess the first thing that I should do is I tried to do two things at once. Let's try and split those up and make sure that that is successful on its own. So the next thing I did is I upgraded pytest Django. These are out of order. I forgot to reorder my tabs. Upgraded pytest Django on its own, and this was fine. So that told me that this was not the problem. I also reran the test suite a bunch of times on each of these pull requests just to make sure, like, it's a flaky behavior. We were kind of seeing it like 1 in every 4 or 5 runs. And so it was pretty easy to just like retry the particular jobs that seemed flaky and eliminate that as a problem. So I was able to upgrade pytest Django on its own. I also then tried to upgrade pytest through each of its minor versions to kind of narrow down what the problem was. I ended up finding that pytest 8.2 was problematic. 8.2 is resulting in similar cascading failures where everything else fails. But 8.1 was fine, so I upgraded to that. But now I wanted to figure out why this broke and ultimately what I can do to try and fix it. So in order to do that, I needed to figure out where in pytest this change regressed. And now normally I would reach for bisect in this, or get bisect in this particular scenario, but it didn't have a good reproduction. Basically, I couldn't reproduce this locally. I tried and tried. We eventually got a local reproduction, and I'll show you that in a bit. I tried and tried, but could not find a way to reproduce this locally, mostly because I didn't really understand why it was happening. Even the reproduction that I had in continuous integration took 30 minutes to reproduce if I was lucky, but sometimes it wouldn't reproduce at all, and it would just, everything would pass, but it was probably still potentially going to fail if some scenario happened. And yeah, I couldn't reproduce it locally. I know I already said that. So get bisect wasn't really a great option for me. I mean, I could have hooked it into get bisect with like some GitHub API and polling, but it was much easier to just manually bisect this instead. So what I did is I looked at all of the commits that had changed in pytest between a version that I knew was bad, 8.2.0, and a version that I knew that was good. So if we have a clone of pytest here, you can do git log, one line. First parent will give you just like the mainline part and not any of the things integrated from a merge. and you can just say 8.1.0 to 8.2.0. Now this actually includes a lot more commits that aren't relevant to the code changes at all. There's a lot of changelog, documentation, tests, etc. fixes that are included in this that I didn't care for. The regression is not going to be committed in some RST change in documentation. So I instead went to limit those commits to just the source directory where pytest actual code changes. And so these are the commits that I was looking at, a much smaller list and something that I could manually bisect to figure out whether things are good. What I mean by manually bisect is, we have this long list of commits. I basically picked one in the middle and forced pytest to upgrade to that particular commit, and then ran it through CI a couple times to see whether it was successful or not. And then I knew, like, if this was bad, then I knew that everything after it was also bad. And then I would do the same process here, where halfway between that commit and this commit, I would pick a commit, test it, say this one was also bad. We know that all of these are bad now too, and so we can narrow it down that way. And I actually, the way I tracked this was in a text document using diff highlighting. It made it very apparent, red and green commits here. And this was ultimately my bisection here. I didn't end up finishing it because I did test this commit and it was green, but I just didn't mark it that way. I ended up finding that this was the particular commit here. And I can kind of show you that process here. Basically what I did is I turned off every bit of the test suite except for a job that I knew was flaky, and then ran that one a bunch of times. So for whatever reason, slice 3 of our test suite was way flakier than all the other ones, and so it reproduced this problem much more often than any of the other ones. 5 was also pretty flaky. I arbitrarily picked 3. But other than that, it's basically just comment out, delete all the other workflows so that CI is only running what I want and not wasting time on other stuff, and then forcibly install a particular revision from Git. And I manually made commits onto this branch that adjusted that version and tested each commit at a time to figure that out. So you can see all these bisect commits here, where I basically changed the, that one's the first one. Let's look at not the first one. Where I basically changed the pytest version over and over and used that and marked commits either green or red in this little diff here. And you can see that it didn't actually take too many times to get to it. 1, 2, 3, 4, 5. Five runs to narrow down a bad change, even though it's flaky and takes sometimes up to an hour and a half to validate change. But ultimately, it's way better than doing each of these one at a time. So still managed to use a bisect, but not actually a true bisect. Okay, so we found the particular commit that caused a problem, which is this change set here. But it was still not obvious to me why this change set mattered at all. The comments on this pull request did mention that this potentially changes how pytest orders fixtures. And so I thought that that was maybe the problem here. Pytest has this helpful option called setup plan. And if you, run it on some random test, test math, that sounds like a test we can run it on. If you're on setup plan, it will tell you the list of, or the order of fixtures and tests and other stuff and the order that they're going to run in, such that you kind of visualize how the test suite executes. It's fairly noisy because, especially in Sentry, it's fairly noisy because there are lots and lots of fixtures, especially when you're dealing with a lot of automatic fixtures for database management and Django and plugins and other stuff like that. So fairly noisy, but I was able to, that's just because I did Q. Fairly noisy, but I was able to look at the difference in setup plan. Now, unfortunately, spoilers, setup plan was not useful. What's that? Plan after and plan before. Okay, so plan after is at 8.2, plan before is at 8.1. If I diff-u plan before and plan after, these are just the output of running setup plan on those two pytest versions. And if we look at the diff here, we already have the diff. Type it to less, that's what we want. We'll notice here that a few, actually, This one changed because I actually switched this from being a session to a module scope fixture. So ignore that part of this diff. That's not the important part. The only change that was relevant was the session teardowns at the end. And again, this one is because it switched to module scoped, but there was actually, it doesn't show it here. Okay, maybe I have the wrong files here. But when I looked at setup plan, the only thing that changed was this fixture got moved to the end. And that fixture doesn't do anything at teardown, so it wasn't, it told me that the fixture ordering wasn't the cause here. I also reverted the fixture ordering stuff because I thought that might have been the problem, and it didn't. I forced the fixtures into the new order on the old version, and it didn't change anything. So that told me that this probably wasn't the problem, and then I had to look somewhere else. But I didn't really know where to look, unfortunately. Like, staring at the output, I kind of felt like maybe some retry was happening, and then maybe it didn't tear down some state properly, and then every test after it depended on that state being torn down, and so it crashed and crashed and burned. All of the R's here are reruns, so anytime a test fails in our test suite, we have a plugin called pytest rerun failures, which, spoilers, will come up later. Reruns the test 5 times. I know, it's absurd to retry a test 5 times, and you wonder why we have flaky tests. It's because they can sneak into the code base with 5 retries. But anyway, that's a rant for another day. So after retries, it seemed like something wasn't being cleaned up. Maybe a teardown fixture wasn't happening, but I didn't really know. But I did notice one thing while trying this out, in particular on this bisection branch. This was just something that I happened to notice by staring at test suite 3 for a while. Is when this test failed, it was always a particular test that flaked first, and then was rerun by pytest rerun failures. Yeah, the output is ridiculous when it actually finishes. Yeah, it was always this test daily summary.py file would always get rerun once, and then everything after it would cascade and fail. I guess not everything, but most things would cascade and fail. And so my thought here was like, okay, I know this test is flaky. It seems to be pretty consistently flaky in this test suite. And every time it fails the first time, it passes the second time. Well, not here, but on the primary branch. It was always failing and then passing. So what this was telling me is that or my guess was, that some other test that ran before test daily summary was polluting this test. Now, I've done a video on test pollution before. Man, how do I even show this? I've done a video on test pollution before, so if you want to find that, this is the video that describes this. Basically, the idea is some mutable state is modified by one test, which impacts the outcome of some other test. And I actually wrote a tool called detect test pollution to try and figure out those pairs of tests. Although in this case, it wasn't actually a pair of tests, it was 4 tests or 3 tests or something like that caused this pollution to happen. But yeah, I'm getting ahead of myself. I ended up using detect test pollution to try and find what pair of tests were causing this to flake. Or I guess not even flake, because it was, you know, like reproducibly failing and then passing. But I wanted to figure out what was causing this. And if I ran this test on its own, it passed just fine. So that's kind of the telltale sign that there's some other test interfering with this test. So I ran detect test pollution, and I will spare you the output because it took a while, because I had to run it against, you know, what, 1,000 tests here? How many do we run in a chunk? Should say right at the beginning. Discovered 1,873 tests. So, well, and I didn't actually have to run all of those because I really had to just run up to the first chunk. So probably a couple hundred tests. But anyway, sparing you that time, I ran detect test pollution, and actually it didn't narrow down to 2 tests. And so detect test pollution actually crashes in this case, and it's like, what? I couldn't find a pair of tests. There must be something else. So I messed with the internals and made it spit out the last time that a failing list of tests happened. And so I was able to narrow it down to not a pair of tests. And I actually haven't debugged the actual pollution here, so I got to do that at some point. But for whatever reason, when these 3 tests run before that flaky test, well, I'm going to call it a flaky test. It's not actually a flaky test. When these 3 tests run before it, then it always fails the first time. And then it always passes the second time. And so my hypothesis was, with this information, I would be able to reproduce the same cascading failure that I could only reproduce in CI. And through a stroke of luck, fortunately, I was able to reproduce the same problem. So basically, I took this list of tests and then the failing test, and then some other test here that was RRRFing. I think I picked, I don't know, this one because it seemed faster than some of the other tests. And lo and behold, I was able to reproduce this same behavior in CI, but only when I used pytest rerun failures. And actually, when I commented on this issue here, being like, hey, I found this in a bisect, I don't know why, maybe you have ideas here. There's some back and forth on down here. Oh, man. There's a lot of discussion on this PR before everything went wrong for me. But yeah, I commented here about that. You know, my hypothesis was that a first test failure interrupts teardowns, and then BlueTech, one of the other pytest maintainers, recommended that it might be the retry plugin. This is the original author. Pytest rerun failures. You know, again, me complaining about retries. And yeah, and then BlueTech suggested that it might be rerun failures. And you'll actually notice one of the things I tried here is disabling rerun failures. And sure enough, yeah, with that off, it didn't reproduce the problem. Okay, anyway, back to this. I had my reproduction. I had these lists of tests. I could run it with rerun failures on a modern version of pytest, and it would always crash. And I could run it without rerun failures, then it would never crash. And so that told me, you know, this commit is definitely the problem. And, you know, rerun failures is definitely the problem, but it didn't tell me why. And so I wanted to understand why. And I actually reached into my toolbox for something that I haven't shown on, I don't think I've ever shown this in a video. This is a technique that's, I mean, not new to me, but will be new to YouTube's for this. I reached for a tool called settrace. And actually I have talked about settrace before, but I don't think I've talked about it as a debugging tool. But basically, the idea behind settrace, it's a CPython, I guess it might be in PyPy also, but the idea behind settrace is it allows you to instrument the execution engine of Python, the virtual machine that runs. And you can intercept, or I mean, not intercept, you can sort of trace lines as they run, or function calls, or you know, all of these things, even down to the opcode level, which, like, if you're making a settrace function that responds to opcode, you're probably going to slow down your code a lot. But anyway, it didn't super matter to me here. And so I got this idea that I could use settrace to find all of the function calls that happened in the working version and then the not working version, and then compare the two. And this should hopefully tell me what function calls are missing in the new version that causes this breakage to happen. Like what stuff is not being torn down. From there, I could hopefully make a reproduction that doesn't involve Sentry at all, and then have a more succinct bug report that I could take to pytest and pytest rerun failures and hopefully resolve this. So I wrote a settrace function, and this actually took a few attempts to get right. So I'm gonna we're gonna spoiler it because this list of files here to basically let me step by step. So I defined my settrace callback. I made sure to open the file outside of the settrace callback. If I did it inside the test suite, ground to a halt, because opening and closing files, lots of syscalls, not lots of syscalls, but syscalls enough that it's really, really slow, especially for every function call, because it turns out Python calls lots and lots of functions. And you pass that callback to sys.settrace. You can, I think this is how you restore it. I don't know. I didn't really care to restore it because it was the end of the session. Made an auto-use pytest session fixture so that it would run during my test run. And I filtered it down to files that I thought would be relevant for fixture setup or teardown. Basically, we have Sentry has a pytest plugin inside Sentry test utils that does some stuff. The tests themselves have fixtures that set up and tear down. Django's test suite or test classes have setups and teardowns, and pytest Django is how we hook up the Django test runner to pytest. So I was hoping to capture all of the function calls that I thought were relevant in here. This, of course, gets way more other function calls that we don't care about, but you know, who cares how much stuff you have here? Actually, you do care a little bit. Before I filtered this down, this generated like like almost 100 gigabytes of function call data, which is nuts. Like Python is it's surprisingly fast given how many functions it calls, but I was basically filling up my disks by tracing every single function call. I also ended up opting out this. I don't think this actually matters anymore because this isn't part of any of these paths, but this was noisy for some reason that I didn't figure out, but I'll probably come back to that at some point. Anyway, with this settrace thing, I was able to trace the old version and the new version, and fortunately, I was able to find, what's the name of the file? The trace.old and trace.new. Trace.old, trace.new. I was able to find what was not happening in the new version. Now, these ones aren't really that important. These are some fixture thing. These weren't happening in the new version. I think it's due to like some like import order thing and didn't actually matter. It wasn't actually the problem here. This is just a thing that checks on our cross database stuff. But if we scroll down a little bit further, somewhere in here, why is it lagging so much? Did I go too far? No. Here we go. This was the first one that I was like, okay, we're not running teardown class. That explains everything that's happening here. Because Django's test teardown, cleans up all the database state and like leaves it in a good state for everything else. And if we're not running that, then all bets are up on anything being successful after that. And so this was only not being run in the new version. And so with that knowledge, I was able to take that and make a non-Sentry reproduction for this particular scenario. Blah, 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 blah. This very simple case here, a class teardown, which just prints class teardown, and a test which fails the first time and succeeds the second time, basically using a global variable here to make the test flaky. And on a working version of pytest with pytest rerun failures, it runs the test, we get a flaky failure, it reruns the test, we get a test succeeding, and then the class teardown occurs. So this is what it should look like. And in the broken version, where I've upgraded to pytest 8.2, the test runs, we get a flaky failure, we rerun it, the test runs, and then there's never any class teardown. And so basically the teardown never occurs and that state is never cleaned up. Now granted, there's no state here. Imagine class teardown actually cleaned up state. So I was able to basically take like a large unknown flaky problem, bisect it down to the commit that caused it, then using the commit that caused it, figure out what behavior changed or like what I was able to observe as a behavior change here. And from that, I was able to make a minimal reproduction. And then just to close the loop, I ended up taking this same minimal reproduction and then also re-bisected pytest and landed on the same commit. In this case, I used git bisect because it took seconds to rerun this test against every version of pytest. Or I guess not every version, but git bisect. And so I was able to find a minimal reproduction and go from there. Unfortunately, we have a little bit of an unsatisfying conclusion to this adventure in that I have not fixed this problem. No one else has fixed this problem. And for now, it is probably just going to remain like this. And I think it's tricky. This is very tricky because I clearly identified a regression. However, this change itself strictly improves how fixtures work in pytest. It corrects some bugs in teardown ordering because basically, if you can imagine fixtures as kind of like a layered pyramid, it should look like a triangle or like a staggered triangle, and you shouldn't have layers that are like shifted out of order. But before this change, some of the larger scoped teardowns would happen in not an order that was expected, or not in like a triangular sort of. So arguably this change is an improvement on pytest, and so we probably don't want to revert it. And arguably pytest rerun failures is a giant pile of hacks, and so in a way, like, it's doing sort of unsupported stuff to pytest internal, so there's only a matter of time before we got burned by some change like this. So likely what I think will have to happen here is pytest rerun failures will need to adjust in some way. There are actually other plugins for rerunning flaky tests in pytest. I was looking into another one called Flaky by the people at Box. Flaky seems good, or at least better. It doesn't have the same failure mode, but Flaky doesn't rerun teardown flakiness. So that's one thing that rerun failures does that we would be losing. And unfortunately, we have some flaky teardowns. So I've got more work to do here, but I think the debugging story was more what I wanted to showcase in this video, and always get back to fixing the problem at some other point. But anyway, that's kind of my journey in starting with a disastrous failure that I didn't understand due to just a simple upgrade, eventually pinning it down to a commit that I identified as a regression but didn't know why. Ultimately figured out what part of it failed, and then was able to take that and make a minimal reproduction and reconfirm that this behavior change between those two versions. Anyway, hopefully you found this useful and found a new tool in your toolbox. If there's anything else you would like me to explain, leave a comment below or reach out to me on the various platforms. But thank you all for watching, and I will see you in the next one.